In this video, we're going to go over section 3.1 from our textbook, which goes over the constant E and continuous compound interest. So we saw in chapter 1 that E is defined informally as some irrational number that can be expressed by this guy here for some large n values. Now we're going to use our limit concept to actually formally define E as either of these two limits here. So looking at this definition, we're defining E by this limit or alternatively this limit here, and both limits are equal to this value here. Alright, so with that being said, let's look into continuous compound interest. So we know that if a principal P is borrowed at an annual after T years at this simple interest, the borrower will owe the lender an amount A given by this equation here. Right, so our amount is just going to be our original amount plus the interest that was gained. So our interest is going to be our original amount times the rate times the amount, how long it's been, times our time. So that is the formula for interest. And then simplifying this by pulling out our principal amount is given by this. So this is the amount owed, just looking at simple interest. However, if interest is compounded a certain amount of times per year, represented by M, then the borrower will owe the lender an amount A given by this here. So this formula is going to be our compound interest, and R over M is going to be the interest rate per compounding period, and then M times T up here is the number of compounding periods. And so the question that we are asking is, let's say that we kept our principal, our rate, and the amount of time fixed as we let M, the number of times we're compounding a year. If we let that increase, we're curious to see if the amount A will increase without bound, so increase forever and ever, go up to infinity, or will it tend to approach some value? Now, before we attempt to answer this question, we're going to look at several values for A, for this amount, when we have this following example here. So if we have our principal, our rate, and our time all fixed, this is our compound interest formula. So we're just plugging in our known values. P is 100, R is 6%, 0.06, and so on. Now plugging in different values for M into this formula that we have, we see that as M gets bigger and bigger, our A values here gets closer and closer to roughly 112.75. So as we make M get bigger and bigger, so approach infinity, our amount A is getting closer and closer to this much here. Therefore, to go back to our original question, it looks like A is tending to approach a limiting value, which is this guy here. All right, so what we're going to do is we are going to introduce a new limit property that will help us look at the limit of this guy as M goes to infinity. So we want to look at the limit of our compound interest formula as M, so the amount of times that it's compounded per year, goes to infinity. All right, and then we will use this new limit property to do this that says if this limit exists, then the limit of this function to the power p is the same as the limit of this function, all raised to the power p. So we'll use that in a moment. But first, what I want to remind us is the definition of the number E. So what we're going to do when we're looking at the limit of our compound interest as M goes to infinity is we're going to try to rewrite this limit like this guy here. And so what they did in this case as you can see here, is that they said S is equal to 1 over N. So S is this guy here. So then this tells us that N is going to be equal to 1 over S. And we can see that's the case here because we have now, instead of to the power N, we're to the power 1 over S. So with that same logic, what we're going to do for this limit is, let's let S equal to R over M. Right. So then this implies that M is going to be equal to R over S. So all we're doing is multiplying both sides by M here and here, and then dividing by S. That's where you get R over S. Now if we were to multiply both sides of this guy by T, so MT, this is the same as this guy here. And lastly, actually let's start with that. So we're going to rewrite this limit as the following. So it's going to be the limit, we have P here, and then we'll have 1 plus, we said that R over M was S, so we're going to have S here. And then we showed that M times T is just going to be TR over S. So we have the power TR over S. And the last thing to note here is that looking at our equation for S is equal to R over M here, our value for S here is actually going to approach 0 for bigger and bigger values of M. So in other words, as M goes to infinity, so as N gets bigger and bigger, our S value is going to get closer and closer to 0. So S is going to approach 0 as M approaches infinity. So here we're looking at the limit of this guy as M approaches infinity. And rewriting this, we're going to look at the limit of this guy as S approaches 0. All right. Now using our properties that we saw in our limit chapter, I forget which section that was, but we know that we can take this constant out in front. So we're left with this here. Now, just using the rules of exponents, we can rewrite this as 1 plus S to the power 1 over S, all to the power TR. Because if we were to multiply these guys, we would get this. And lastly, using our new limit property here, we get all raised to T times R. All right. And then simplifying this, we know that the limit of this guy as S approaches 0 is just equal to E. So our formula becomes P times E to the power R times T. All right, and as you can see down here, that is our continuous compound interest formula. So if a principal P is invested at an annual rate R, and this will always be expressed as a decimal, and if this is compounded continuously, then our amount A, and the amount at the end of a certain amount of time, is going to be given by this guy here. So let's look at an example. So what amount to the nearest cent will be in an account after 5 years if $100 is invested at an annual nominal rate of 8% and it's compounded annually, semi-annually, and continuously? So first, if we look at compounded annually, so we'll do some color coding. Remember, M is represented or represents the number of times that we're compounding per year. And since we're compounding annually, M is equal to 1. So we're going to use our compound interest formula, which is this guy here. So let's just write this down for us. All right, and then plugging in all of our known values, we know that we're going to start with $100, so P is 100. Then we have 1 plus our R over M. R is 8%, so that is 0.08 since we're expressing this as a decimal. And this will be all over 1 because we're compounding annually. And this will be times 1, and then T is 5 years. So T is 5. Right, so then we'll get 100 times 1.08 to the 5th power. And then this is roughly $146.90. All right. Now, if we wanted to look at compounding semi-annually, in this case, M is just equal to 2, and we'd use the same compound interest formula, but now M is 2, and then get our answer. I'll let you guys do that one on your own, and then jump directly to compounding continuously. So in this case, we're compounding continuously, so we're going to be using our formula for that, which is given by this guy here. And again, we're starting with $100. P is 100. R is 8%. And our time is 5 years. And then plugging this into a calculator, we get roughly $149.02. Right, so not too bad. You just have to be careful with what's being asked in the question. Now let's look at an example where we want to graph the growth of an investment. So if $5,000 is invested in a Union Savings Bank 4-year CD that earns 5.61% compounded continuously, graph the amount in the account as a function of time for a period of 4 years. So we know we're compounding continuously, so we automatically know we're going to be using this formula here. And we want to graph the amount in the account as a function of time for a period of 4 years. And so that's why I have this graph already set up for us. And so essentially what we want to do is get a function for A, and then look at our output values for T0 through 4, because we're looking at a period of 4 years. So we know A is going to be equal to, we have $5,000 originally invested, so that is what P is. Then we have E, and then our rate is 5.61%, and as a decimal, that is 0.0561, and that's being multiplied by T. So let's look at values of A, which is a function of T, as we have 0 years, 1, 2, 3, period of 4 years. So first, we'll plug in 0 for T, so then we get E to the power 0. E to 0 is just 1, so we get 5,000 times 1. So dollars. All right, now plugging the rest of these values into a calculator, we're going to get, and we're going to be rounding to the nearest dollar. All right, so plugging 1 in for T here, we get $5,289. Plugging 2 in for T, we get $5,594. Plugging in 3, we get $5,916. And then plugging in 4, we get $6,258. Okay? Now what we want to do is graph the amount. So what we'll do is we'll use these points here and plot them on this graph here. So at t is equal to, so this is a of t, and this is t here in years. So at 0 years, we start off with 5,000. The first year we get 5,289, so somewhere around there. Second year, 5,500, so somewhere around here. Third year, we get close to 6,000, so somewhere around there. And then the fourth year, 6,000, almost 6,300, so maybe somewhere around here. So our graph would look something like this. All right, so that's how we would graph the growth of an investment over a certain time period. And the last thing we're going to look at is computing growth and doubling time. So for this example, we're looking at how long will it take an investment of 10,000 to grow to 15,000 if it is invested at 9% compounded continuously. So since we're dealing with compound interest, compounding continuously, we know we're going to have to use this formula here. But if you look back at our question, it's asking how long it will take for this to happen. So this means we want to find t. All right. So we'll plug everything into our formula for continuous compound interest and then solve for t. So we know that our amount will be 15,000. And we're starting at 10,000. So 10,000 is going to grow to 15,000 at a rate of 9%. We want to figure out how long that'll take to happen. So the first thing we can do is divide both sides by 10,000. So we get 1.5 on the left side, and then we still have e to the power 0.09 times t on the right-hand side. Now remember, our natural log function is the inverse of our exponential function, so we can just take ln of both sides, and these guys will cancel. So then we're left with ln of 1.5 is equal to 0.09 times t. So this, when this cancels, these exponents come down. So we saw this in chapter 1. And now fully solving for t, we'll divide both sides by 0.09. So t is equal to ln of 1.5 divided by 0.09. And plugging this into a calculator, this is roughly 4.5 years. So it'll take about 4.5 years for an investment of $10,000 to grow to $15,000 at a rate of 9%. And the very last thing we'll look at is computing doubling time. So actually this problem in particular is going to be tripling time. But in the book, there's an example just like this, but it's looking at doubling time. So we're asked, how long will it take money to triple if it is invested at a 5.5% compounded continuously? So again, we know we're going to be using this formula. And just like the previous example, we want to find t. Now, the trick here is that we're looking at how long it will take money to triple. So that means whatever we started with, whatever our p is, we want our a to be 3 times that. So what we can do is rewrite A as 3p. Okay, so our final amount is just going to be 3 times what we started with. So this is our new formula here. And then we do have our rate is 5.5%, so just plug that in. All right, now the p's on both sides here cancel, so we're left with 3 is equal to e to the 0.055 times t. And then we can do the same thing we did in the previous example to use the fact that ln and e are inverses. So we get ln of 3 is equal to 0.055 t. And then solving for t, we get t is equal to ln of 3 all over 0.055. And so then plugging this into a calculator, this is roughly 22 years. So this means that it would take roughly 22 years for money to triple if it's invested 5.5% and compounded continuously. All right, so that's it for this video.